Well, good morning, everybody. And first of all, sorry for not being able to attend live to the conference. However, I'm recording this video so that I can still present my work, which in this case is focused on the non-invasive analysis of cultural heritage samples through digital imaging. My name is Roberto Saez, and I'm an assistant professor of analytical chemistry at the University of Valencia. Well, when we talk about or when we delve into the analytical investigation of, in general, cultural heritage samples, there are different issues or different variables that we are interested in studying. For example, we can address the state of conservation. That is, we can study how well conserved, how well the sample is currently in the museum or in the building or whatever. Or many of the analytical tools can actually give us information about that state of conservation. Then there is also the artistic technique. If, for example, we are talking about, I don't know, a picture, we can gather information through through analytical research, through analytical investigations, regarding how the artist actually painted the picture itself, right? So all these techniques actually leave a fingerprint a chemical fingerprint in the picture, and nowadays we can have that information mainly through spectroscopy, but not only, and we can then imagine or like reverse engineer how the artist created it. And then we can, of course, talk about the composition itself, like what is it made of? What is it that is in this case, in that picture? In this regard, it's especially interesting for pigments, because when an artist is painting something, it's giving its color, and that color is given because of a certain pigment, right? So that information about the composition is actually quite interesting. In that regard, when we are talking about frescoes, about wall paintings, there are two main topics, two main issues that we have to address. First, which is the pigment itself, that is, which is the chemical species that is actually giving the color to the spot. And then you cannot see it, but it says binder. That's a little bit related to the artistic technique, and that's basically how the artist actually stuck that pigment to the wall. So if we are talking about, as I said, wall paintings, that pigment needs to be stuck. It needs to be retained in the surface of the wall. In that way, in that direction, there are actually different techniques. So that fresco technique is actually or relies on the formation of calcium carbonate that's building like a network within in which the pigment can be stored, or it can be, for example, organic binders like egg, and then it's acting like a glue for the pigment to be on the wall. So all these investigations, maybe the most interesting one when it comes to elemental analysis is X-rays fluorescence. Mainly because this is a portable instrumentation that we can actually carry to the wall painting without needing to sample, to destroy the wall painting. As I said, this technique is actually really interesting because it's giving us information about the elemental composition. However, we have to consider that these techniques actually give us information only in the case of inorganic pigments. Then there are also organic compounds, organic components, which we can address, for example, through infrared spectroscopy. In that regard, there are also portable near and near spectrometers that can actually give us information about the vibrational components, the vibrational elements of the molecular molecular components. In that regard, there is also Raman spectroscopy and molecular colorimetry, which are, as infrared did, giving us information about what are the compounds that are actually in the piece of art. So we are talking always about pigments. We are then talking about color. So to study color, maybe the most common technique is a spectrophotometer. This is a portable reflectance spectrophotometer, which is basically giving us the chromatic coordinates of the spot that we're measuring. But there is also the possibility, there is also the option to measure that sample through digital analysis. So in this regard, smartphone cameras are actually a device that take the color information of whatever they are capturing. They apply some transformations to the images, but we can model those transformations so that we can get the final color coordinates. So you can start to see that we are doing something similar between this instrument, and we are aiming to build something similar to the colorimeter, by using the smartphone camera. So what did we do in this work? Basically, we tried to replicate the wall paintings, and as it was very difficult to do it in a wall itself, we did it in a reduced scale. So using a ceramic tile, we built the different layers of mortar, first of all with a more coarse sand, then with finer sand, and finishing by a plain layer of pure lime. This is then the white canvas on top of which we can actually paint the different spots. As you can see, this is one of the replicas we built. We tried to use different pigments. More specifically, we used 3 red pigments, which are minium, these you can see here, cinnabar, which are these ones, which are mercury-based, and iron, which are these ones, is actually hematite. Then we also tried some mixtures of binary mixtures of compounds. And of course, we tried to have like a whole hue, like a whole palette from more intense colors to more pale colors. The objective was basically to build a calibration model which contained as much information as possible within it. As I was saying, we are aiming to use the smartphone as an analytical device, but these are not originally built so that they are analytical devices. Then the most concerning problems that we have to address are, first of all, the environmental lighting influence. That is, the camera is actually recording the color of whatever it is looking at, but that measurement is really influenced by the lighting environment that we have. So if there are changes in that lighting environment, we will have differences in the final color coordinates. As we will be using those color coordinates to build chemometric models, we need to consider what is going on in that lighting environment. Then we have also to consider that each and every device and each and every company will build the smartphone differently, and the sensors will be slightly different, and mainly the color processing or the color processes that are included within the smartphone are actually different. That means that the smartphone will capture the light, and it will be, of course, influenced by the lighting environment, but it will also be influenced by whatever the smartphone is doing to that information in a second background. Like, we cannot know what the hell is going on inside, and we will always get the final information. So we have to find a way to model all those variables so that the final information is actually reliable analytical information. We have to model the environment, the experimental conditions, and we have to model whatever the smartphone is doing with regards to the color coordinates. To do that, what we basically did was we measured a color chart, which actually includes a grayscale line, which is this one here, and then some other color patches. The idea is that these color patches actually cover a quite rich chromatic space. So this color patch, we will measure it by a reference colorimeter, which will yield CLF color coordinates. These CLF color coordinates are basically like points in this graph here. It will give us this point, for example, telling us that it's this red, this yellow, and we have to imagine a third axis coming out of the screen, which will be the lightness. Sorry. So these are the reference values, and we will then have the images from which we can extract the RGB parameters. Of course, these RGB parameters are the ones that are influenced by those two variables that we were talking about. These RGB coordinates are actually influenced by the lighting environment, and these RGB coordinates are influenced by whatever the smartphone is doing. Okay? So, as we know the real values of these patches and we know the final RGB parameters, what we will be doing is correlating both. So we will build a polynomial model that is actually considering the real information, the obtained information through the smartphone, and then correlated it. It will calibrate the response of the smartphone. The idea behind this is that when we acquire the image of our picture, of our wall painting, we will only have the RGB parameters because we are building this model, we are building this method so that we don't need the colorimeter, so that we can go to whatever the wall painting is, we can take a picture, of course, with the calibrate on the side, and then get the RGB parameters. We can include those parameters to the model and get corrected CLF descriptors. So with this approach, what we are doing is getting a model that we can build in the lab, and then we can apply that model to real samples in whatever the environment. To do that, we tested the general commercial X-Rite color chart, which is the one here. And then we also thought that we could build ad hoc, like color tailored calibration chart. To do this, what we did was basically to print with commercial printers different color spots. So we built different color spots, and we using like a little bit of cardboard, we built something similar to the general or commercial calibration chart. Regarding the chemometrics behind this, what we built was a super vector machine model, which is basically drawing borders. So we are creating what it's called a margin, which is basically a border between two classes. The model is trained so that it can actually accept some misclassifications. These two red spots are misclassified, but that's a margin we can allow the model to have. The margin, the border, will build in the direction so that it maximizes the amount of correct classifications, right? So then basically what we will have is like a model telling us whatever sample will fall here belongs to class A, that will be a pigment. Whatever samples land here, are found here, will be classified as class B, so that will be a different pigment. And these models will be built on the basis of the corrected CLF parameters. So these are the results basically that we published in this contribution, in this very recent contribution, published in the Journal of Dyes and Pigments. Basically, first, what we did was to test the different charts, right? Here you can see the result with the commercial color chart, and here you can see the results using the tailored color charts. What we are plotting here is the difference between the real values and the corrected values. So the more to the right that we find the distribution, that means that the average values that we obtain with our model are more different to the real ones. So basically, we are aiming to have models that yield distributions close to zero. That means that samples are actually quite similar to the real value, right? So first of all, we can compare only looking at this graph that we have 3 degrees. If you remember, I talked about a polynomial model that correlated RGB values with CLF descriptors. So that polynomial model can actually have degree 1, degree 2, or degree 3. Of course, as we increase the degree of the polynomial, the complexity is increased and the results are improved. You can see here the green distribution is actually quite bad. This is a threshold value we established, which is 3.5 units. So the green distribution, which is a degree 1, is actually quite bad. Then we have the purple one, which is degree 2, which is actually way better than the degree 1. And then we have degree 3, which is more complex, but it's actually way better. However, we decided to stick to the second degree polynomial, basically because the improvement that we got upon the implementation of the degree 3 model was not sufficient to compensate for the potential overfitting of the model. So if we increase the complexity of the model unnecessarily, we will have greater risk of potential overfitting. So we decided to stick to the degree 2. And then comparing between the color chart, the commercial ones, and the ad hoc ones, we saw something similar, actually. The distribution of the degree 3 are way better. So overall, we decided to stick to degree 2. Here, what we are addressing is, okay, how good are these ad hoc samples, these ad hoc charts when compared to the commercial one? And to do that, to answer that question, we are representing here the plots as obtained by the colorimeter. These are the samples that we measured. These are the reproduced values as obtained by the commercial color chart, and these are the distributions of the samples as obtained by the tailored, the specific ones we created. So basically, we are aiming for similar distributions on the vertical axis, right? We need this distribution to be similar to this one, and this distribution to be similar to this one. What we obtained was that these tailored color charts were not good enough. The distributions, the colors that we got were not so similar to the real ones. And actually, the ones we obtained using second degree polynomial on the commercial color charts were actually way better. This was potentially given the fact that we printed this with commercial printers. And we maybe lacked some parts, some regions of the space, some regions of the color space that were actually not represented in the model, in the calibration. So then if a sample falls in that area, it will be extrapolated and the result will be all over the place. So this result, although initially promising, we found out that it would need further improvement. And this is a summary table of all the super vector models. So basically, we built one for the yellow color, we built one for the blue, and we built one for the green. These are parameters that are optimized throughout the models, like the distribution of those borders. These are complexity of the borders, and this is the cost, like how much do we allow the model to fail when classifying. Overall, the important part is that we obtain a cross-validation error using only the trained subset, like the calibration subset, and the errors were below 4.5%. And if we used an error of prediction, that is, if we predicted a sample that was not originally included in the model, in the calibration of the model, the errors were 2.9, 2.2, and 5.7%. So this is actually really good. This means that it will always work better, the classification using this smartphone-based method, than we would do with the naked eye. If we had to classify a spot of a wall art, of a wall painting, only saying this is red enough, and this should be then, I don't know, hematite, we will fail way more times than this objective model. And this is the area under the curve, which is basically like the distribution of how good the model is. So if this is close to 1, this means that it's a perfect classifier, and if it's close to 0.5, it means that it's totally random. So values very, very close to 1 actually point towards a really good classifying model. And as I said, these values were actually really good. So as I said, this is the job that we published. So if you want to check any details, you can find them there. And for concluding, we have developed like a digital image based method to objectively characterize historical samples, or sorry, historical pigments in wall paintings. We tried 2 different color charts, and despite finding a good idea with the tailored, with the ad hoc color chart, we found that it was way easier for us and for any restorer to use exclusively the commercial ones. When it comes to the chemometric models, with regards to the chemometric models, we were able to check that the super vector machine, the super vector classifier, were actually really good and performed really well when identifying different pigments exclusively using corrected digital color parameters. And thus, this method is actually really interesting because it can be applied only using a smartphone and a little color chart, which is something that you can carry basically anywhere and apply with minimal technical knowledge with a very affordable cost of the whole process. So thank you very much for your attention, and once again, sorry for not being able to attend. And if you wish to forward me any doubt, don't hesitate. This is my email right here, and I hope to see you in another conference. Thank you.